explaining physics in heels. Today's lesson with Professor Diva, Physics for Everyone. Today's lecture is Creating the Universe. In today's lesson, we're going to cover a short introduction to particle physics, how particles come together to build matter, and we're going to talk about the birth of the universe. As I mentioned in my introductory video, I am a particle physicist, meaning I study matter at a very, very small scale. You might know this already, but matter is not continuous. We don't just have this big fluid of matter. What we have is small bits of matter called particles that come together, and when you put enough of them together, you build a large-scale picture of matter. I, as a particle physicist, am responsible for studying those particles at their very small scale and to study them one by one. As you can imagine, that's pretty difficult. You might have also heard the term quantum, for example, in quantum mechanics. So what is a quantum and what's the difference between a quantum and a particle? That's a really good question. A quantum is the smallest part of something. So for example, the quantum of the written language is the letter. The quantum of the spoken language is a sound. The quantum of a heels choreography is the move. The quantum of matter is, of course, a particle. And so quantum mechanics is the study of those small bits that make up matter. So then what's the difference between particle physics and quantum mechanics? In fact, quantum mechanics was developed at the beginning of the 20th century when scientists still believed that matter was made up of just atoms and nothing smaller than that. But as we have proven, atoms are themselves not the smallest bit of matter. They're themselves made up of smaller bits called particles. So quantum now is more of a historical term, whereas particles are right now to be believed the smallest bits of matter possible. We cannot go deeper, we cannot go smaller, hence why we call them elementary particles. Elementary means that we cannot split them up further. In order to dance in heels, you need two big things. You need a good sturdy pair of heels, and then you also need some dance moves to perform in heels. Matter functions in the same way. We organize elementary particles into two big categories. First of all, we have matter particles. These are the particles that we make the physical matter out of. And then we need some interaction particles. You have heard of interactions before. What we particle physicists call interactions, other physicists call forces. So why don't particle physicists use also the term force? That's because a force implies a big object interacting on another big object, such as a human pushing a chair or a heels dancer pushing on a pair of heels. Whereas particles don't really push on one another. What they do is they interact with one another. So they just influence one another from a distance. Fun fact, forces are also made up of particles. Everything is made up of particles, hence why I really like this field. Because if everything is made up of particles, we can use particle physics to explain everything. This organization of all of the particles in the universe is called the Standard Model. Standard because we believe that all matter to be governed by these principles. So let's start with the interaction particles first. You might have heard already that there are four big interactions or forces in this universe. The four fundamental interactions or forces in the universe are gravity, which you know very well. It is this force of attraction between bodies that have mass. Then we have electromagnetism, which is an interaction of attraction or repulsion depending on the electric charges that the bodies have. Now, there are two more fundamental forces in the universe that only take place on a very small scale, and that's the scale of elementary particles. We have the strong nuclear force, which is my research, which is the force or interaction that keeps matter together. The reason matter doesn't just explode into nothingness, but stays together and forms more and more complex, larger scale matter because of the nuclear strong force. Hence why we call it strong. Lastly, the nuclear weak force is a force or interaction that changes the flavor of particles. It's almost like it gives them a makeover. If you can actually believe it, this is all that the universe can do. All other forces or interactions in the universe are made up of these four interactions. For example, the force of friction, that is the electromagnetic force between the atoms of one surface and the atoms of the other surface. The force of tension in a spring, same thing. It is the electromagnetic force between the atoms that make up the string. Arguably, almost all of the forces in our daily lives are a form of the electromagnetic force. So much phenomena can be explained with the electromagnetic force. It is remarkable. And that's because those two last forces are on a very small scale. The electromagnetic force is on what I would call a medium scale. So a scale of atoms. And then gravity, of course, is on a very large scale. Planets are not affected by the nuclear forces because planets are so big. Planets are also not really affected by the electromagnetic force because the electromagnetic force is not strong enough at that level. But planets are incredibly affected by gravity. So we can think of gravity as being a very large-scale force. Particles that are so incredibly small don't have enough mass to really experience gravity at a pretty fundamental level. So we usually think that gravity doesn't really affect particles. We know it does, it's just that the effect of gravity on particles is so incredibly small, we choose to ignore it. That's why you might have heard of this. The standard model is not really compatible with gravity. We are in dire need of a recombination of gravity and the standard model of elementary particles. That's the research field of a lot of scientists who work in what we call quantum gravity. Quantum, because remember that quantum is the smallest unit of something. Now let's talk about what particles need in order to interact through these forces. In order for two particles to interact, they need to have the charge that corresponds to that particular interaction. Think of it like this. If you want to send your friend a reel on Instagram, you both need to have an Instagram account in order for you to send and for the other one to receive an Instagram DM. That Instagram account is what in physics we call a charge. You have already heard of an electric charge, right? If a particle has electric charge, then it can interact through the electromagnetic force. If a particle has mass, then it can interact through gravity. So mass, we believe to be the charge of the gravitational interaction. Now for the strong nuclear force, we have another name for its charge, which I find quite cute. We call it a color charge. A color charge has nothing to do with colors as we know them. It's just a cute name that physicists have come up with in order to keep track of the charge needed for the strong nuclear force. As you know, the electric charge has two possibilities, either a positive charge or a negative charge. Well, the color charge has three possibilities, which we denote red, green, or blue. Again, it's just how Instagram has a personal account or a business account or a content creator account. Same thing, you have three options for three different types of color charge. What about the nuclear weak force? This also has a charge of its own, which we call a hypercharge. But I'm not gonna get into it too much because it can get funky. One final point about the interactions is that each interaction has a particle through which the interaction takes place. If I want to make someone move, I give them a ball, and by catching the ball, that person is gonna fall back. Same thing with forces. If I want to interact with another particle, I need to send that interaction particle. You might have absolutely heard this name, but the electromagnetic force, the particle of that, is the photon. So light is the electromagnetic interaction. The nuclear strong force, its particle name is called a gluon. Glue because, just like glue, it keeps matter together. Isn't that cute? The nuclear weak force has what we call a W or a Z boson. Gravity has what we call a graviton. However, we have thus far not discovered a single graviton. So we just believe that they exist, but we don't really know for sure. We just need to perform more measurements and more experiments to finally discover a graviton. We talked about interaction particles. It's time we talked about matter particles. And there are two big categories for matter particles: Leptons are particles that can interact through the electromagnetic force, so they have electric charge, and through the weak interaction. The most famous lepton that you know of is the electron. The electron is electromagnetically negatively charged, as indicated by this minus sign here along the E, which comes from electron. Quarks can interact through the electromagnetic, the weak, but also through the strong interaction. So, unlike leptons, quarks have an extra property where they can form bigger, more stable matter because they can stick together through the strong nuclear force. So the matter that you know of, like atoms, is mostly built up from quarks instead of leptons. Let's talk about it. Quarks are organized in 3 big pairs, which we call generations. It is just a name, it has nothing to do with age. In each generation, or in each pair, we have 2 particles, one of them being positively charged in terms of the electromagnetic interaction, and one of them being negatively charged in terms of the electromagnetic interaction. In the first generation, we have the up quark, which is positive, and the down quark, which is negative. In the second generation, we have charm and strange, and in the third generation, we have top and bottom. I do want to preface this by saying that Americans call these top and bottom, whereas Europeans call them truth and beauty. I'm sorry to say this, but I think the European name is prettier. I think truth and beauty is nicer than top and bottom, but I guess we'll just work with it. Interestingly enough, leptons have charge -1, whereas quarks have fractional charge. For example, the up quark actually has positive 2/3 charge, and the down quark has negative 1/3 charge. If I put one up quark, another up quark, and one down quark, what do you think I get? Let's think about it. The electric charge of the up is positive 2/3, plus the positive charge of the up quark is again 2/3, and then I have to subtract the negative charge of the down quark, which is 1/3. 2 plus 2 is 4, minus 1, that's 3. 3 over 3, that is positive 1. So this structure right here, up, up, down, has electric charge positive 1. I think you know what this is. This is what we call a proton. So would you look at that? We just constructed from 3 quarks our first proton. That's what happened at the Big Bang too. The universe was in this very, very dense and very hot conglomeration of quarks and leptons. So you had flying around a lot of up quarks, a lot of down quarks. As the universe started expanding, because the Big Bang, which was this big explosion, launched the universe out into space and it started expanding, the universe started also cooling down. By cooling down, the particles, the quarks, weren't so agitated anymore, and they started moving more slowly. By moving more slowly, they started coming together and forming bigger and bigger matter, such as the proton. And as the universe got bigger and bigger, the protons, together with the electron, came together to form atoms. So the universe started with just a bunch of quarks. It expanded, cooled down, and then those quarks and leptons came together to build atoms. Now, there is another particle that you have heard of that is constructed from 3 quarks. What if we had up, down, down? Let's do some calculations. As I said, this has charge positive 2/3. The down has negative 1/3, and then the down also has negative 1/3. So let's see. 2 minus 1, that's 0. So this structure right here has a 0 electric charge. Do we know a particle that has 0 electric charge? Absolutely we do. As the name suggests, this is a neutron. So a proton and a neutron are incredibly similar. The only difference is this middle particle right here, which for the proton is an up quark, and for the neutron it is a down quark. Neutrons were also formed at a particular stage when quarks started coming together to form protons or to form neutrons. Now let's build our first atom. As I said before, we need an up quark, and we need another up quark, and we need a down quark to make a proton. Now, between those quarks, we have the strong force. So this is the strong nuclear force which keeps those quarks together in a structure which we call a proton. Now we can have another structure also built by the strong nuclear force, which would be between an up and two down quarks. And we have already established that this is what we call a neutron. The neutron is also built by the strong nuclear force. Hence why I use the same color between those two particles, even though this is a positively charged proton and this is a neutral neutron. In fact, the pro in proton means positive, while the neut in neutron means zero or neutral. This is why I think the strong force is brilliant. If we were to only have the electromagnetic interaction, the proton and the neutron would feel no attraction towards one another, because one of them is positively charged and the other one is neutral. Because this one is neutral, it cannot interact through the electromagnetic interaction, because it's almost like it doesn't have an Instagram account to receive DM. However, the neutron and the proton can interact, the two of them, with the strong nuclear force. So they do stay together because of the strong nuclear force. And what happens when a proton and a neutron come together? They build a larger structure, which we call a nucleus. Hence why the name nuclear strong force, because it is the strong force that builds up nuclei in the universe. Now let's look at the charge of a nucleus. The proton is positive, the neutron is neutral, so the whole nucleus has a positive charge overall. The electron, as you remember quite well, is negatively charged. So it has a negative sign right here. What happens between a negative charge and a positive charge? They attract one another electrically. So this is the first instant where we have the electromagnetic interaction build matter together. That's what I mean. The nuclear force is on the small scale of a nucleus, whereas the electromagnetic force is on the middle scale of an atom. That's because when the electron and the nucleus attract one another, together they build an even more stable structure we call an atom. And this is the way that atoms are constructed from elementary particles. Pretty cool, huh? Thank you so much for watching. Your support means the world to me. If you want more physics, be sure to subscribe and to hit that bell icon so you can be one of the first people notified when I upload a new lecture on a really fascinating topic. And if you want to get to know me better, check out my Instagram, Physicist in Heels, where I post reels daily. Well, see you next time.